Hi everybody. Today we're going to be looking at some polymer structures. So I got some feedback from the midterm evaluations that you wanted some more practice, some more in-depth explanations of this stuff. So I'm going to try to do more of that. That will be this time. It'll actually be more in class during lab because we have a little bit of a shorter lab next week, so we'll be doing some more practice problems in lab. So today I'm going to introduce you to these types of molecules called polymers and how we kind of deal with them theoretically, how we draw their structures and talk about them. And then next week we're going to look more at applications. So what does it mean? How do plastics work? Why do they work the way they do? What are some of the issues around there? So, and then during all of that, you'll also be, of course, making your bioplastics and analyzing them in lab. All right, so let's get started. So first of all, let's talk about what this term means, polymer, and what a polymer is. A polymer is a name for a very large molecule that is made up of repeating smaller molecules that can react to each other. So there's a couple different ways to do this. I guess let's just write this definition first. So a polymer is a large molecule made of repeating small molecule units, we'll say. And these repeating small molecule units are called monomers. So the polymer, poly means many, the polymer is the whole thing, the monomer is each individual one that it's made up of. So let's just kind of look at this before we get into the actual molecule structures. Let's just kind of look at it, what we're generally talking about. So there's a few different ways that this happens. One way is if you imagine a molecule, this is not oxygen, I'm just drawing a circle. Let's say there's a molecule and it has a couple pieces on it. Let's say it has a piece that looks like this and a piece that looks like this. And the square piece on the left can fit into the socket on the right. So imagine this is an actual physical piece that you could put together. So you could imagine then that you could have many of these and they would be able to kind of bond in this way. So every time you make a connection between two of the molecules, you still have the connecting pieces on either side. And so you're still able to continue to connect more and more. So then we grab another one, and another one. And each time there's still space for it to keep reacting. So you can imagine this sort of continuing on and on. So it's this one piece that can react with itself over and over again. So in this case, the single unit, any of them really, the single unit that keeps repeating is the monomer. And this whole big thing is then the polymer. So that's one way it works. Another way is these could actually be on different molecules. So let's say you have one molecule that has a square on both sides, and then one molecule that has a this bracket kind of thing on both sides. Actually, let's give it a different shape. Sorry, getting too many shapes here, but I think it'll make sense. All right, so we've got our blue circle molecule. I also don't want to just refer to colors because I know some people can't see the colors. So we've got our blue circle molecule with the two square connections, and we've got our red triangle molecule with the two bracket connections. So then these two could react together and make something like this. Right, so let's say those two fit together. And now we have essentially the same situation as we had in the first example, where you could have this thing continuing on with more of the same. So you could have more of these molecules coming in to react, and you kind of continue to do this over and over again. And so you're building this chain up. All right. So if you now imagine, you've got a solution or whatever, a sample of just like thousands of these things, or millions of these things, or billions of these molecules, you can imagine that it can grow quite large and quite quickly. And so these types of materials, polymers, have really changed everything about how we live our lives. If you look around in any environment that you're in, pretty much, unless you're in the woods or something, most of the materials you see are probably coming from polymers. So anything that you might describe as a plastic or a synthetic material, really anything except natural materials like wood, metal, glass, things like that, are going to be made out of polymers. So I'm just looking in the classroom here. You know, the desktops are all going to be some sort of polymeric structure. The cloth on the seats is all polymers. The more obviously plasticky stuff is. The epoxy on the floor is polymers. You know, really all the stuff that I'm looking at. Even some of my clothes, I'm not entirely sure what these clothes are made out of. There's probably some cotton and wool, which is not a plastic, not a synthetic polymer, but certainly if there's some stretchiness to your clothes, you've got some of those. You've got things like nylon, rayon, polyester, polypropylene, any kind of like high-tech breathable type fabrics. Those are all going to be polymers. So these things have really kind of taken over. So now let's go from our general idea of what these things kind of are to specifics of how we draw them, starting from actual molecules. All right, so we're going to look at two broad categories of polymers: addition polymers and condensation polymers. Some other names you might hear for these: addition polymers are known as chain growth polymers, and condensation polymers are known as step growth polymers. As always, these notes are in OneDrive, so you can follow along there, actually just live, or you can take your own notes and then check later and make sure you got everything right. All right, so we'll first start looking at the addition polymers. Addition polymers they usually come from alkene monomers, which are carbon-carbon double bonds. There are others as well, but for our purposes, those are going to be the most common. So the very simplest addition polymer comes from the molecule ethylene, which is just a carbon double bond carbon with two hydrogens on each carbon. So C2H4 ethylene. Now, ethylene is a gas, and it doesn't just polymerize by itself the way we might have drawn up here. In fact, most of these, the way it works is you have some relatively stable monomer, and then you introduce it to something called an initiator, which kind of gets it going and allows it to react. And we're not going to go through the whole specific mechanism of how that works. We're just going to say some sort of initiator reacts with this, activating this. And we can think of one thing we can think of happening here is the initiator breaking the double bond. And as we learned a lot earlier, carbon always has to have 4 bonds. So if that double bond somehow gets messed with, now these carbon atoms that no longer have enough bonds are going to be very reactive. And so the way that they can react is they can react with another of the same molecule. So we have this ethylene here missing its double bond, and that's actually going to connect to another ethylene. I'll use a slightly different color to show that. And then that continues over and over and over And you can see from the colors, hopefully you can see a contrast even if you can't see the actual colors, that this kind of keeps going over and over again in these individual monomer batches. So we lose the double bond and we connect the monomers together. And it essentially looks like, at least the way we've drawn it here, like it's never going to end, because you're never going to have a carbon at the end that has enough bonds. And so what really happens is in the solution, it terminates somehow. So maybe two big chains come together and happen to connect to each other. Or the molecule grabs an atom off of the solvent or somewhere else, or it comes back on itself and connects in a big circle. There's lots of different ways that it can terminate at the ends. But because these things are so long, we kind of don't worry about that, and we usually just say, well, these things are just going on and on and on. And we might use the like ... notation like this to just show that they're going on and on. But there's actually a little bit better way to do it, and that is to look at one of the monomer units and put parentheses around it, kind of like we did with the condensed structures. So we could say, for example, let's just pick this one. That's one monomer unit. So we could draw this polymer as just that monomer unit without the double bond. And the way that we express it continuing on and on and on is to draw lines out past these parentheses. And then if we want to, we could specify a specific number down here of how many of these units there are. But for polymers, there's usually a big variability in what those numbers are. And so we might just say n, meaning this thing just repeats over and over again some number of times, right? N is often kind of a stand-in for just some number. So we've got this thing repeating n times over and over and over and over again. And this polymer would be called polyethylene. So we've got ethylene monomer, polyethylene polymer. Okay? And this is actually a super important material. If you look at the bottoms of certain containers, I don't know if we have one here. Let me see if I can find one. Hold on. All right, I'm going to try not to drip on all my stuff, but this is the soap container. And if I don't know if you can see that, but there's a little triangle in there with a 2 in it, and it says HDPE. And that stands for high density polyethylene. So if you've seen containers like this, they're usually a little squishy. Milk jugs, another good example. That is polyethylene, what we just drew. So while we're looking at that, if you look at the back side of any of your plastic stuff, it has the symbol on it, which we're going to talk about more next week, but it kind of looks like this. It has this symbol, and then it'll have a number in the middle, and it'll say like HDPE. And this is a label of the type of plastic it is. Now, the tricky part about this is that this symbol looks a whole lot like something to do with recycling, right? This is essentially the logo for recycling. And a lot of people assume that that means that that particular material is recyclable, but it's not true. The law, or it's required that these containers made of plastic be labeled as to what type of plastic they are. And the plastic industry just decided to use this symbol as a way of labeling what type of plastic it is to try to convince people that their materials are recyclable and that they actually can be recycled. But that's not necessarily the case, and we'll get into that more next week about how most plastics really can't be recycled or aren't recycled. And so that's, if you thought that meant that those things are recyclable, you know, that's fine. Pretty much everybody does. That was designed to trick us that way, but it doesn't. It doesn't mean that. All right, so this is polyethylene, and let's talk about a couple other ways of drawing this. So again, please, if you haven't had a chance to really master the drawing structures stuff, the line structures, the condensed structures, please do so, because again, we're going to keep using that every time we talk about different kinds of molecules. So, case in point right here, instead of drawing all these hydrogens out all the time, we could draw this as a condensed structure or a line structure. And as things get bigger and more complicated, that can be really, really useful. So for this particular one, polyethylene here, we could try a condensed structure, which would look really pretty much the same, except we would condense the hydrogens down onto the carbons. And then we could also do that as a line structure. This one can be a little bit trickier because it looks like there's 4 carbons here, 1, 2, 3, 4 in the line structure. The reason that there aren't is because, again, these bonds coming off of the parentheses just kind of mean it keeps going and going. So the only 2 carbons are inside the parentheses, 1 and 2, in all of those different types of structures. Okay, let's look at a couple other types of polymers, of addition polymers with similar structures. So another common one is polypropylene. So propylene has 3 carbons, and we'll draw out the full Lewis structure here first. It has 1 double bond between 2 of the carbons, and then an additional carbon coming off like that. So this is propylene. If we want to make polypropylene, we have to polymerize this. But notice that if we extended this out from here, from this carbon on the far right, a couple reasons that wouldn't work. Primarily, there's no extra space for bonds here because of all the extra hydrogens. This carbon can't make another connection because it already has its 4 bonds. So we know that we can't connect that way. And if we were to get rid of a hydrogen or move it over or something, we would end up with the same thing as polyethylene. That's not quite what happens. So what happens in polypropylene, and what you should see as kind of a pattern going forward with addition polymers, is we're always going to be connecting from either side of the double bond. So whatever else is connected coming off of the molecule, it's that main carbon-carbon ethylene type double bond that's going to control how it polymerizes. So when we draw the actual polymer here, after polymerization, we're going to have the chain part is going to look pretty much like ethylene. So we're going to have something like that that's then going to connect to the next one, and so on. The difference here is now this extra carbon, I don't know if it's really extra, the 3rd carbon here, is still connected. So that's now down here, or up, or however you want to draw it. And the next molecule is going to have that same thing. So the main polymer chain going horizontally here is the same as with ethylene. The difference is that now every other carbon has this other CH3 connected. And that's going to keep going again in both directions. So if we want to draw that in more of a condensed way, let's look at the condensed structure actually here first. Let's draw this exact same thing just in a condensed structure, because I think this is one of the examples where the condensed structure really makes it clearer because you can see how stuff is lined up better without all the extra hydrogens around. So exact same thing in condensed structures would be CH2, CH, CH3. Then over to the red one here, we've got CH2, CH with the CH3 coming down here, and then we're extending in both directions like that. All right. So then if we want to go to this parentheses notation, we just pick one of these units and put it inside the parentheses. All right, so that's our one of the repeating units. And there's our parentheses with the N. And if we want to show that as a line structure, we can do the same thing. So there's our main chain, and then we've got that CH3 coming off there. So same type of chain. And if you look through some of the examples in the linked reading, you'll see all of these addition polymers kind of looking about the same. All right, so let's try another one. Oh, sorry, so this would be then called polypropylene. Polypropylene is another important plastic material. Most food containers are made out of polypropylene because polypropylene doesn't contain a lot of plasticizers, other types of chemicals that can be a problem when food is sitting in them. So polycarbonate kind of had an issue for a while with a molecule called BPA that could leach out of the plastic and get into the food, and polypropylene doesn't have that. So things like the disposable plastic food containers, Ziploc containers, things like that, not the bags, but the more rigid containers, those are usually polypropylene. Anytime you want to make things really not take in water, polypropylene can be a good choice. So things like ropes that are meant to get wet, like marine ropes and things like that, are sometimes polypropylene. Also clothing that is meant to wick away moisture or get the moisture away from you, it won't saturate with water, and so it passes that water through, and so those things are sometimes made from polypropylene. All right, the last addition polymer we're going to look at is polystyrene, and this one we're going to do all inline structures, so we can practice that. So this one's a bit bigger. It starts with a bit bigger of a molecule. This is styrene. And now we have a little bit of an issue because we have lots of double bonds here that could potentially polymerize. So you're just going to have to take my word for it that it's this one up here that actually does the polymerizing, and the rest of the molecule is just kind of along for the ride. So we're going to extend from here and there. That's going to be our structure, and then every 2 carbons we'll have this big ring, which is called a benzene ring, hanging off one of those. So the way to draw this is we're first going to draw that polymer chain, and with line structures it's actually quite easy because we know that polymer chain is just going to be that zigzag line that we keep seeing. So something like this. I don't know if I did quite enough here, make it an even number. And then we can add our other things that are connected. Now, to make sure we're adding the other things properly, it's a good idea to just number the carbons off. It doesn't matter where you start. Let's just go 1, 2, and 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. All right. And every time we see a 1, just like in our monomer, we're going to show the styrene coming off the bottom of that. So 1 has this, 1 has this. I shouldn't have drawn this so many times. I'm gonna get tired. Okay, and so on. We should have just gone with a couple. It's quick to make the zigzags. It's not so quick to draw all these rings, but that's fine. So then if we want to look at kind of like the smallest unit, the smallest repeating unit of this structure, that would be like, we can pick wherever, but let's just say here, right? 1 and 2. And then we can draw that as a single repeat unit. Like that. And that's indicating that this thing is repeating over and over and over again. This is polystyrene, which is a really common polymer. If you can tell from the name, it's most associated with styrofoam, which is this molecule or this polymer with a bunch of air in it or a bunch of gas in it to make it all, take up a lot of space and very low density and very good padding. But polystyrene is used in a lot of other things too. A lot of disposable food stuff like disposable forks and spoons and knives, the disposable cups like the red Solo cups, those kinds of things, polystyrene. Polystyrene is generally not recyclable, and so that sometimes is a confusing problem because polystyrene gets mixed in with other things that are a little bit more recyclable and can cause some problems there. In some places, polystyrene is recyclable, and you just kind of have to look and see, but polystyrene is actually so cheap and easy to make. It takes such little energy to make it that it's really not worth recycling from an energy or a cost standpoint. And so it is worth recycling from a waste standpoint, but that means someone has to pay to do that because it's not economical to do so otherwise. And that's kind of an introduction to the problems we're going to see in polymers and plastics when we get into this next week. All right, so those are some examples for some addition polymers. I'll have some practice problems for you for working on how to draw these structures. Read the section that's linked, please, about polymers and some of those structures. I don't want to get into the condensation polymers, the other category, just now, because I feel like it'll be more useful if we do it together actually in person. So we're going to do that next week in lab, and then we will talk about it a little bit more online with some of those waste issues as well. All right. Well, thanks everybody, and I'll see you in lab. Bye.